Now, delta S of the universe is a great way to figure out if a reaction is going to occur or not, if it's spontaneous or not. But chemists really like using delta H, all right? Enthalpy is so important for lots of different reactions. And so Gibbs, down there in the lower right, was one of the great first of the American chemists. He came up with this idea to rewrite the second law of thermodynamics just a little bit. Now, delta S of the universe equals delta S of surroundings plus delta S of system. But we also saw how delta S of the surroundings equals minus delta H of the system over the temperature. And delta H is what chemists use so much. So what Gibbs did is he substituted in delta S of the surroundings equals minus delta H over T, and then he messed around with the system a little bit. He basically multiplied everything through by negative T. So then he had negative T times delta S of the universe equals delta H of system minus T delta S of the system. And basically then he, in the long run, created a new type of thermodynamic quantity, which is now called Gibbs free energy, delta G, and delta G equals minus T times delta S of the universe. So, long story short, a better version for chemists is not to use second law of thermodynamics, but use delta G equals delta H minus T delta S. This is called the Gibbs equation because Gibbs was the first person to figure it out. And why chemists like this better is you can use delta H values directly. So all those delta H product minus delta H reactants, that's going to go right there in the delta H term. But you can do the same thing with delta S. Delta S is going to be products minus reactants for entropy values, and it also shows explicitly the temperature dependence of the entropy values. So that's what's kind of cool. The only strange thing about it, if you look at this little table right here, is that we're going to look for the opposite signs as we did for delta S of the universe. Now, if the entropy of the universe is increasing, that's spontaneous. But because of that negative part right there, that negative T, that means we're going to be looking for delta G's which are less than zero. So a negative delta G is the same effect as a positive delta S of the universe, and those are always going to be spontaneous. And likewise, if you have a delta S of the universe which is less than zero, that means your delta G is going to be greater than zero, etc., etc. So chemists use delta G a lot more than delta S of the universe, and we're going to be actively looking for negative delta G's. Those are spontaneous. Those are the ones that are going to occur. Positive delta G's are non-spontaneous, and those are less likely to occur. So delta G is kind of the chemist's version, if you will, of delta S of the universe, and once you get used to it, it's actually pretty chill to use. So this Gibbs free energy is basically the total energy change for the system minus the energy change in disordering the system. So the energy change of the system, that's delta H, and you're essentially subtracting the entropy in disordering the system, which is delta S. But along the way, the temperature becomes a big factor because temperature times delta S is the factor you'll use to help calculate delta G, and we'll see the effects of that here in a little bit. But if you have an exothermic reaction with a negative delta H and an increase in entropy, a positive delta S, your delta G is going to be negative all the time, and negative delta G means that reaction is going to be spontaneous and product favored. So if you calculate a negative delta G, your reaction is going to happen. It's spontaneous. On the other hand, you can have endothermic reactions with positive delta H's. You can have negative delta S's, entropy decreasing, and those delta G's will be positive all the time. And positive delta G means you're not going to have a reaction which is going to occur as readily. So positive delta G means the reaction's not spontaneous. That's going to be more reactant favored. So if you want your reaction to go, you're hoping for exothermic and an increase in entropy, because those will always be spontaneous. On the other hand, if your reaction happens to be endothermic and with an entropy decrease, your delta G will be positive, and those will be a lot more difficult to make happen. If both delta H and delta S are the same sign, then temperature is going to be a huge factor in determining the spontaneity, i.e. determining if the reaction will occur or not, all right? And high temperatures will make one set of conditions spontaneous. On the other hand, the other set of conditions, low temperatures, will make it spontaneous. This is just something to keep in the back of your mind. And this is one reason why this equation is pretty cool, because it shows how temperature times entropy is a factor, and you have to compare it to delta H. So let's calculate the Gibbs free energy, the delta G, for this reaction. Magnesium oxide minus would be the product. Magnesium solid and half an oxygen would be the reactant. And we have here the delta H and the delta S values, okay? Now, one thing to be aware of is that delta H is almost always in kilojoules, and delta S is almost always in joules. And you can't add kilojoules to joules directly. It would be like adding a meter to a kilometer. All right, they're different types of units. So you have to turn meters to kilometers or kilometers to meters to make that happen. And it's the same thing with these. You have to turn one of them into the other. Now, because all of our answers are basically kilojoules per mole, let's turn the delta S into kilojoules. And to do that, you divide by 1,000, which means you basically move the decimal over 3 places. So if you do the math, delta H, that number, minus T delta S, well, T is going to be the Kelvin temperature, 298. We'll multiply it by minus 0.10836, turn it into kilojoules. If you do all of that, you get answer B, minus 568.9 kilojoules per mole. This is a negative delta G, so that means it's spontaneous. That reaction is going to occur. Pretty cool. So magnesium will react with oxygen to make magnesium oxide. We know that because delta G is negative. It's spontaneous. It's going to happen. This is an overview of the Gibbs free energy equation and what the possible values mean. And remember that if delta G is negative, that's spontaneous. That means the reaction is going to occur. Delta G that's positive means non-spontaneous, reactant favored. That's not as likely to occur. And here's the 4 different combinations of delta H and delta S that are possible. So exothermic, i.e. negative delta H and positive delta S, means you're going to have spontaneous delta G, i.e. negative delta G values all the time. If you flip them around, that'll always give you positive delta G values, which are reactant favored. And then again, if delta H and delta S are the same type of sign, i.e. if they're both negative or if they're both positive, then the temperature is going to play a factor. And we'll talk about that here in a little bit to see what's happening. So here we have a reaction. It has a negative enthalpy and a negative entropy. So what can be said about this reaction? Product favored at all temperatures, low temperatures, it's product favored, high temperatures, not product favored, etc., etc. 42 is a bad reference to a silly movie. Sorry about that. If you look at the Gibbs free energy, a negative delta H is going to help make delta G negative, all right? Because if negative is delta H, then delta G will be more likely negative. On the other hand, negative delta S times a negative right there, negative times negative means positive. So the entropy here is not helping delta G to be negative. As a matter of fact, delta S here being negative is going to make the reaction less likely to occur. So what we have here is a temperature dependent situation. Notice that both delta H and delta S have the same sign. They're both negative. And if they're both negative or if they're both positive, that means temperature is going to play a factor. Now in this case, entropy is negative. And so if the temperature is big enough, then negative T delta S will be to overpower delta H. So at higher temperatures, this reaction will have a positive delta G. On the other hand, if temperature is lower, then T delta S will not be able to overpower delta H, and you'll still have product favored spontaneous reaction reaction, i.e. a negative delta G. So for this reaction, low temperatures will make T delta S smaller than delta H. And in those situations, then, you will have a spontaneous or product-favored reaction. On the other hand, as T starts getting big, then the delta ST term will overpower delta H. And delta S is not making Gibbs free energy negative. It's going to make it positive. So at quote-unquote high temperatures, this reaction will not be spontaneous. Now, low and high are very relative, all right? Low temperatures could be like 2 Kelvin, or it could be 2000 Kelvin. It's hard to say. But past that temperature, that's when things will change, and that's the important part here. So at the lower temperatures, your delta G will be negative, and at the higher temperatures, your delta G will be positive. And that's the effect of T delta S versus delta H, if you will. There are two methods for calculating delta G. The classic method, the one that's probably best and used the most, is you find delta H and delta S separately, and then you use the Gibbs equation. However, if you do have all of the delta G values, you can do something similar to what we did with enthalpy and entropy. So the delta G of a reaction is equal to the sum of the delta G of products minus delta G of reactants. This is the last column in the mhchem.org/thermo table that we haven't used yet. We've used enthalpy since Chem 222. We used entropy in tables earlier, and the third column is the Gibbs free energy values. And you can see from the sample table there in the lower right some delta G values. Like delta H, delta G values for elements in their standard states are equal to 0. But after that, delta G values can be both positive and negative. So there's diamond, it's a positive number. On the other hand, carbon monoxide has a negative delta G. So you kind of have to look the values up. I think more of them are negative than positive, but honestly, you should look at them to make sure. So either of these methods are great. The delta H minus T delta S is probably better. It usually gives more reasonable answers than delta G products minus delta G reactants, but we'll do both of them in this class, and so you should know how to do both of them as well. Here's an example where we'll use delta G products minus delta G reactants. We're figuring out delta G for the reaction diamond plus oxygen going to carbon dioxide. So for this reaction, we take the delta G of the product, CO2, and subtract the delta G of the reactants. But you'll notice that only diamond is given, there's no O2. That's because delta G for the elements in their standard states, all those values are 0. Now diamond is given because carbon's natural form is not diamond. Graphite is much more common. You can go buy a graphite pencil pretty easy and it's not too expensive. Diamonds, of course, are much more. So that's why diamond is given. C of graphite would be equal to 0, and C of O2, which is the normal form of oxygen, is equal to 0 as well. So products minus reactants would be minus 394.4 minus 2.9 and minus 0 because O2 doesn't have a value. This comes out to be answer A, minus 397.3. So you can see all the math down there, what happens. This is a negative Gibbs free energy value, so that means this is spontaneous. And what this means is that your diamonds are going to go to carbon dioxide eventually too. So earlier I stated that diamonds are going to go to graphite, and that's true. On the other hand, this also shows diamonds will one day turn into carbon dioxide. That's what the negative value means. But again, don't panic. Don't go selling all your stuff because kinetically, this is a very, very slow reaction. It's not going to happen in anybody's children's lifetimes. So just realize science tells some information, but you have to use a practical part about it as well. Here's an example of turning graphite into carbon dioxide and finding delta G. So similar to with diamond, it's also spontaneously going to occur, i.e. the delta G of negative 394.4 is a negative number, and negative numbers are going to happen. So again, this is why graphite as well will all turn into CO2 one day. And that's why CO2 is kind of a problem child for us right now with greenhouse gases. It's so easy to form, and it's hard to get rid of once you have it. All the delta G values, the free energy of formation values for elements and their standard states, will equal 0. And again, product favored, greenhouse gases. In this section, we're going to start talking about what's called enthalpy-driven and entropy-driven reactions. And if you have an enthalpy-driven reaction, that means you have a negative delta H, exothermic, because negative delta H's contribute to a negative delta G, and negative delta G's are spontaneous. So if you have an enthalpy-driven reaction, you have a negative delta H. Entropy-driven reactions have positive delta S values, because positive delta S times negative T makes that whole term negative, and that contributes to a negative delta G. So positive delta S reactions will be called entropy-driven.
When we pour sodium carbonate into hydrochloric acid, it dissolves rapidly to produce aqueous sodium chloride and gaseous carbon dioxide. In this case, entropy increases, and the reaction is energetically favored to occur. It is both enthalpy and entropy-driven.
So this reaction is both enthalpy-driven and entropy-driven. And if you look at that reaction, gases were created, and gas creation almost always implies positive delta S. So that means that reaction is definitely entropy-driven. On the other hand, wow, a lot of energy came out, bubbling and all kinds of stuff. That's negative delta H. That's exothermic. So that means that reaction is enthalpy-driven. Energy was given off. Delta H will be negative, and entropy-driven, the gases being formed there will make delta S turn positive. That reaction is going to happen almost all the time. However, not all spontaneous reactions will have both favorable delta H and delta S values, and we'll look at some of those here. Acetylene is used in torches when people weld a lot. Acetylene reacts with oxygen to make CO2 and water. And if you've ever seen an acetylene torch, you can see that, wow, they light up. You're not supposed to look at them directly, so look away. But anyway, let's think about acetylene's combustion here a little bit more. If you calculate the enthalpy of formation for this acetylene reaction, it'll be delta H of products minus delta H reactants, so 2 CO2s and a water minus C2H2 and 5/2 O2, it comes out to be very exothermic, minus 1,238 kilojoules per mole. And again, negative numbers for enthalpy imply that enthalpy wants this reaction to go. This is an enthalpy-driven reaction. But if you do the same thing for delta S products minus delta S reactants, you get a negative 97.4 joules per Kelvin. And negative delta S's are not entropy driven. You need a positive delta S to make that entropy driven. So in this case, if you look at this long enough, you have 2.5 moles of oxygen and 1 mole of C2H2, so a total of 3.5 moles of gas going to 2 moles of CO2 and 1 mole of gaseous water, going to 3 moles of gas. So 3.5 moles of gas going to 3 moles of So 3.5 moles of gas going to 3 moles of gas, that's not making entropy happy. Entropy wants more disorder, and we're actually organizing it, going from more moles to less moles. So that's why the delta S value here is a negative number. So this reaction is enthalpy driven, but it is not entropy driven. You need a positive delta S to make it entropy driven. On the other hand, if you combine these at room temperature, 298 Kelvin, delta H minus T delta S, make sure you turn delta S into kilojoules per mole, you end up with a delta G, which is minus 1,209 kilojoules per mole. And that means this reaction is spontaneous, product favored. Delta S doesn't want this reaction to go, but delta H is able to overpower it and make it happen. So this is an enthalpy-driven reaction, and it makes the reaction spontaneous, but this reaction is not entropy-driven, and that's an important consideration.
In the center beaker is water at room temperature. To this we add solid ammonium nitrate. The ammonium nitrate dissolves. Usually, a reaction that occurs so readily is exothermic, but we see from the thermometer that this reaction is endothermic. the temperature of the water drops significantly. This reaction is not favored energetically, yet it still occurs.
So I've been using this example a lot. This is an example of an endothermic reaction. So that means delta H is going to be a positive number, and positive delta H's do not make this an enthalpy-driven reaction. So enthalpy does not want this reaction to go. However, you are seeing the reaction occur, all right? The solid is dissolving. So that means delta G is a negative number. It means it's spontaneous. Well, if delta G is negative, but delta H is positive, then that means that delta S must be positive, all right? Because something is making delta G negative, and it sure is not delta H. So we're going to hope here in a little bit when we calculate it that we're going to find a positive delta S because something must make this reaction occur. We're going to see a positive delta H because it's endothermic, and overall delta G should be negative. So let's look at the math. Delta H, products minus reactants, sure enough, comes out to be endothermic. Energy is needed to make this reaction happen. This reaction is not enthalpy driven. On the other hand, delta S, products minus reactants, comes out to be positive, 108.7 joules per Kelvin. This is an entropy driven reaction as predicted, all right? And entropy here is what's making this reaction happen because, as you can tell, the solid is dissolving. If something happens, delta G is going to be negative. So delta G here, when you figure out delta H minus T delta S, make sure delta S is turned into kilojoules, etc., minus 6.7 kilojoules. So looking at these values, this reaction is spontaneous. Delta G is negative. Spontaneous means it's going to occur. This reaction is entropy driven because delta S is positive, and positive delta S contributes to negative delta G. But this reaction is not enthalpy driven. Delta H is positive, and to have an enthalpy-driven reaction, you need a negative delta H. So try to figure out these terms and how they work. They do help chemists to kind of figure out what the driving forces are, what makes reactions occur, and what makes them not occur. This reaction is product-favored, even though it's an endothermic reaction. Entropy, if you will, saves the day and makes this reaction okay.